Hi, with this chapter, we are going into rotational kinematics. So this is the first chapter that we will talk about rotational motion. We will start with angular position, velocity, acceleration, and then we will move to rolling motion and other things related to kinetic energy and moment of inertia. So let's get started. So to understand rotational motion, it's best to go with analogies between the linear and angular motion. They're very useful. For example, in rotational motion, think about this as a bicycle wheel. So it's not moving to the left or right, up or down. It's only rotating around its axis. So this is the axis of rotation. So it's rotating this way or this way. So there are two options. So if you choose a point, let's put a point here. So the position, the angular position of this point, it can come here, it can come here, and during the rotation it will move. So the angular position of this point, we can quantify it by angular position theta. So it will be just like the linear position x, but in this case, everything is angular, so it's angular position. Now, where is the 0 point? Okay, so when in the linear case, if you have a coordinate system like this, let's say x and y, then you could say this is the 0 point. But what about here? Well, that's arbitrary, just like in this case. Remember, you could put your coordinate system anywhere you want. So it's the same thing here. You can put the 0 line anywhere you want. So that's arbitrary. But usually the reference line is chosen as the 0 angle. So this reference line, this is usually, most of the people use this as the 0 point, 0 angle. So this is usually called 0 angle. You don't have to choose it. You can choose this as 0 angle and this point. So if you choose this point, let's start from here. If you choose this point as 0 angle, then this angle, the angular position here would be pi over 2 radians, or 90 degrees. Or if you choose, let's say, this point to be 0, let's say theta equals 0. So this point would be theta equals negative 90 degrees, and this point will be 90 degrees. So it's up to you, but the convention is, what most people do is just take this line to be theta equals 0 and measure all the angles in the counterclockwise direction. So if you go this way, the angles are positive, but if you go this way, the angles are negative. So now we always talk about radians when we talk about angles. So there are a couple options. One of them is the degrees, the other is radians. Now, pi radians is 180 degrees, right? 2 pi equals 2 pi radians equals 360 degrees. So pi radians is 180 degrees. So this whole thing, you can call it pi radians or 180 degrees. So this is a unit, degrees, or radians is also a unit. So pi radians means 3.14 approximately radians equals 180. So within 180 degrees, there are approximately 3 radians and a little bit more. So then 1 radian, so the whole thing is 180. So 1 radian is approximately this much angle. Of course, you need 3 and some more, so this part is 0.14, and it goes like this. So this pi, you can either use pi, you can either say pi radians, or you can say 3.14 radians for 180 degrees. And you can calculate if pi radians or 3.14 radians is 180 degrees, then 1 radian is approximately 57 degrees. So this is 57 degrees, approximately. In reality, it's 57.2 something, so it has the fractional part as well, but that's good enough. In addition to radians and degrees, there's also another unit which is called revolution. Revolution, 1 rev is at 360 degrees, or 2 pi radians, and you know 2 pi is approximately 6.3 radians. So 1 rev means this bicycle wheel, it makes 1 full rotation. So that's 1 revolution. Also, rev, degrees, or rad, or radians, are units of angle, but they are dimensionless. That is, they are not made up of fundamental dimensions of meter, kilogram, and second. So they're units of angle, but they are dimensionless, which means they are not made up of these 3 fundamental dimensions. The convention to choose the counterclockwise direction. So counterclockwise is this direction. This is counterclockwise, and this is called clockwise. Why? Because if you think about the clock, the second hand or minute hand or the hour hand, they go in this direction. So this direction, this way, is clockwise, and the other direction is counterclockwise. So the convention is, so we have to call either one positive and the other one negative. So the convention is you call counterclockwise as positive. So this is positive direction, and this is negative direction. So if this wheel turns this way, then its angular velocity will be positive, as you can see here. If the wheel turns clockwise, then its angular velocity is negative. And here, omega is the angular velocity. So it quantifies how fast this wheel rotates in this way or the other way. So from here, you can understand that it can be positive or negative, depending on if it's rotating counterclockwise or clockwise. So let's start with arc length before we move to angular velocity, angular acceleration. So let's start with this one. So the arc length is this distance here. It's called S. And if you want to find this distance, it's basically you have to multiply the angle with the radius. But there's one important point here. This angle, it should be not in degrees of rev, it should be in radians. So if this formula gives me this length, then I can calculate the whole length, and I know what whole length is. It's circumference, and I know from the primary school it's 2 pi r. Let's see if this formula works. So r is r here, and the whole angle is 2 pi degrees, and you can see it's here 2 pi r. It really gives me the circumference. So if you want to calculate this length here, let's say this length, and if it's 90 degrees, so this will be S equals R times. Now I have to write down, so this is 90 degrees, but I have to write it down in terms of radians. So the whole thing is 360, and that means 2 pi radians. So then 90 degrees is pi divided by 2 radians. So this distance then is r times pi divided by 2. Again, you have to use radians in this formula. So in some of the formulas, you will be able to use radians, degrees, or revs, but in this formula, you have to use necessarily radians so that you get a correct result. Let's move to average angular velocity now. Now, if you remember from linear motion, the average velocity or speed, it would be delta x divided by delta t. So the change in position divided by the time passed. So the angular velocity is similar. Now, if you remember, for instead of x in rotational motion, we had the angle. So this will be then for angular velocity, which is omega. Then instead of x, I'm going to have theta. So this will be delta theta divided by delta t. And you know that you can interpret this as the final theta minus initial theta. So this theta, delta theta, it could be revs, degrees, or radians. And delta t can be seconds, minutes, hours, years, any time unit. So here, as we talked before about that angle is dimensionless. So if this thing is dimensionless, it still has a unit. See, these are the units, but it doesn't have any dimensions. So the dimension of angular velocity will be 1/time, because this is dimensionless. There's time in the denominator, so the dimension will be 1/time. So in SI units, its unit will be 1/s. But of course, there will be some angle, so it will be angle unit. So it will be either radians per second, or it could be revs per second, or it could be degrees per second. So here, the angle, delta theta, doesn't have to be between 0 and 2 pi. So it can be any positive or negative numbers. For example, if the wheel rotates 2 revs per second, then we can calculate the angular velocity like this. So 2 revs, 2 revs means it makes 2 full rotation. So we write 2 revs here, and divided by the time. In this case, it's given as 1 second. So the angular velocity, you can say it's 2 revs per second, or you can convert 2 revs to 4 pi. Then you can say 4 pi radians per second, or you can convert it to degrees. You can also say 720 degrees per second. See, these are all angle units. Now, the other concept that's related is period. Period means the time it takes for one full rotation. So you have to pay attention here. So delta t can be in general anything, right? It can make 5 rotations, half rotations, 100 rotations. So delta t will depend on that. But if we are talking about one full rotation, only one rotation for 2 pi, then the time for that will be t period. So now let's write again the formula for the angular velocity. So if we write uppercase t, that means one full rotation. So what will be delta theta? Well, one full rotation in radians, it's 2 pi. So we got a formula here, omega equals 2 pi divided by t, or I can rewrite it as t equals 2 pi divided by omega. Here, so radians per second would be the unit of omega. The unit of the whole thing will be, so here you have radians, and in the denominator you have radians per second, so the whole thing will be in seconds. So this relation is the relation between the period and the angular frequency. So let me give you an example. So the period of the Earth rotating around its axis, its own axis, is 24 hours. So it's 1 day, 24 hours. So let's calculate Earth's angular speed. So we are going to use this formula again. So angular speed is 2 pi divided by time that it takes for one full rotation, which is also period. So 2 pi divided by, what is that time? It's 24 hours. If you want, you can just leave it as is. You can say 2 pi divided by 24, you can calculate that number, and it will be radians per hour. That's also valid. But if you want to find everything in SI units, which is radians per second, then you have to do a couple more steps. So you have to convert this 24 hours to seconds. So hour means 60 minutes times 60 seconds. And if you do this calculation, the angular velocity of the Earth rotating around its own axis is this small number, radians per second. And similarly, you can calculate the Earth's period of the Earth orbiting the Sun. So in this case, you can also calculate. So if we call this one a day, you can also calculate the angular velocity or speed for year. So what is the angular velocity? So this number is for this angular speed. So let's call it omega day. There's also this angular speed related to the year, related to that, the orbital motion of the Earth around the Sun. So that would be, you can calculate it in the same way. So it will be 2 pi divided by 365 days. Again, you can leave it as is. You can call this as radians per days. But if you want to convert it to SI units, then you have to convert years into seconds. And there's one more related concept, that's frequency. And the relation between the frequency f and the angular speed is this relation. So the difference is just 2 pi. Now, we talked about angular velocity. It was this formula, omega equals delta theta divided by delta t. Now, this was like velocity. Now, we move to angular acceleration. We will show it with alpha. In the linear case, let's go with analogies again. In the linear case, you would do delta v divided by delta t, so the velocity divided by delta t. So in this case, we will do the same thing, except instead of linear velocity, we will use angular velocity. And this becomes our formula for angular acceleration. Let's do an example here. So we have a windmill here. As the wind dies, a windmill that was rotating at 2.1 radians per second. So this is the angular velocity initially, right? Let's call this omega I. Begins to slow down with angular acceleration. So this is the angular acceleration, alpha. But because it's slowing down, if you remember, if it's slowing down, the acceleration would be negative. So 0.45 radians per second squared. How long does it take for the windmill to come to a complete stop? So how do you calculate it? Well, we are going to use this formula, except I'm going to have delta t on the left-hand side, because that's what's asked. And it will be delta omega divided by alpha. And delta omega is basically final angular speed minus initial angular speed divided by alpha. So we are going to use this formula. So to be able to use this, so we know what alpha is, negative 0.45. We have to calculate final minus initial angular speed. So initial is this one, and final, because it will stop, is 0. And if you calculate delta omega, you will find it's just negative 2.1 radians per second. Now I can plug this number here and the acceleration here. And if you do the calculation, you will find 4.7 seconds. So this was rotating with some initial angular speed. And because the wind died, it cannot keep rotating, so it will stop with certain acceleration, or you can call it deceleration. So the question was, how much time would it take? So this is the time that it would take. Now, in the linear case, this is like the problem, let's say there is this object. It was going with certain initial speed, and at some point it stops. Maybe there's some friction or other force, and it would give us so the initial velocity, and it would give us the acceleration, the linear acceleration. So from here we would use v final equals v initial plus at. So it's basically the same idea. So in this case, if you put v initial to the other side, so it will be delta v equals at. Or if you want to pull t from here, it's delta v divided by a. And if you compare these two equations, they are exactly the same, except we are using different variables for the acceleration and the angular speed in the rotational case. But the analogies hold, so everything is pretty much the same, except instead of linear motion, we have now rotational motion. So let's think about a little bit more the angular velocity. So in the previous slide, I talked about this, the analogy between this formula, the linear case, and the angular case here. Now, if you remember, the velocity could be positive or negative, including the initial velocity and the final. So the same thing here, the angular velocity can be positive or negative, and also the acceleration can be positive or negative. So if you remember our definition, if the wheel or the disk, if it rotates this way, that would mean positive, because this is positive angular speed or angular velocity, because this is counterclockwise, and we define counterclockwise as positive. So this is positive angular speed. So if it rotates this way, and if it starts to slow down, so it's rotating this way, but now it's starting slowing down, maybe there's a force or friction, something. Now, what about what happens to the acceleration? Is it positive angular acceleration? Is it positive or negative? Well, if it's slowing down, then it should be negative. This is negative. And in the following slides, I will show you all 4 cases where both the angular velocity and the angular acceleration can be positive or negative. Now, when we did linear motion, I had given you these 4 possibilities. So if the car was going this way to the right, and if the velocity and if the acceleration, if they're in the same direction, that would mean the speed of the car would increase. Or we can go this way. If the velocity is given to the right, and if someone tells you the speed is increasing, then you could infer that the acceleration is also in the same direction. Now, look when speed increases. Acceleration and velocity, they are to the right. And also here, speed increases. Acceleration and velocity, both to the left. And now look at the cases where the speed is decreasing. Acceleration and velocity, they are in the opposite directions. So the conclusion here is the speed increases if acceleration and the velocity are in the same direction, regardless if the car is moving to the right or to the left. So if they're in the same direction, that means the speed will increase. The same thing we will see here in rotational motion. So let's take these. These two are rotating clockwise, so the angular speeds are positive. Okay, so angular speeds are positive. If the acceleration is also in the clockwise direction, then which is the case here, it's also clockwise. So omega is clockwise, and angular acceleration alpha is also clockwise. So in this case, the angular speed is increasing. Remember, if there is acceleration, that means there is a force. In the next chapter, we will learn about torque, which is rotational force. So if there is acceleration in this way, that means there is a rotational force, which we will call torque in the next chapter. So there is a force, and because the velocity, the angular velocity is also in the same direction, so the speed will increase. Now, in this case, the speed is positive, but the angular acceleration is negative. That means there's a force. You can think of this as friction, or someone is applying a force in this way. So because here the angular speed is clockwise, but the angular acceleration is counterclockwise, because they're in the opposite direction, you get decreasing angular speed. Now look at here, both are negative, but which means clockwise, but they're in the same direction, so you get increasing speed. Here you get clockwise angular speed, but counterclockwise angular acceleration. And because they are, again, in the opposite direction, you get decreasing angular speed. So to summarize the analogies between linear and rotational kinematics, x is like theta. So x and theta, they are similar. They are both for position. These are position. These v or omega, they are velocity. And a or alpha, they are acceleration. And when you compare these, and you will see there is a one-to-one analogy between linear equations and the angular equations. So even this one, so final squared equals initial velocity squared to acceleration, delta x. And we have the same thing here. Now this time, final angular acceleration or angular speed squared equals initial angular acceleration squared plus 2 angular acceleration times the difference between angular position. So basically put the word angular between the variables here, and you will get the second part of the table. Now for this one, we can write it as delta theta, which means theta final minus theta initial. Now you have to be careful about this. So let's say we have a wheel, okay? And let's say there's this point here, and this point, let's say it makes one full rotation. So if you just look at the positions, you know, it comes back to the original position, which is 0 degrees. So if you write 0 minus 0, you get 0, but that's incorrect. Because it made one full rotation, the correct answer here is 2 pi. Or if it makes 2 full rotations, then the correct answer is 4 pi. If it makes half rotation, the correct answer is pi. So just be careful. If it makes more than 2 pi angle, makes rotation more than 2 pi angle, so these don't necessarily mean the final and initial angle, but you have to consider the change, the total change, which can be more than 2 pi. Okay, here's an exercise. We had a tire that has initial angular velocity 300 RPM. RPM means rev per minute. Usually in motors, like electric motors, they usually use RPM. So, and it rotates counterclockwise. So counterclockwise means this way. And omega is 300 RPM. If the angular acceleration is 50 rev per minute squared, clockwise, now the acceleration is clockwise. So it's in the opposite direction. So we have to use alpha. Now, clockwise direction is negative, remember, so I have to write negative 50 rev per minute squared. what is the final angular velocity at t equals 7 minutes? Okay, we will use this equation. Now, the final angular velocity is this one. Remember, this meant final. So we are going to calculate it. Now, the initial angular speed is 300 RPM, 300 rev. You can write RPM or you can write rev per minute. Okay, and plus you will write now -50 rev per minute squared times 7 minutes. Now, if you realize that I have not converted minutes to seconds, so I did not go to SI units. In this case, it's okay to use these units per minutes because first you have an equal sign. So if you write minutes here, if you write quantities with per minute or per minute squared here, then the answer will be again per minute. So if you are fine with it, then that's fine. If the answer is asked in units of revs per seconds, then you can later convert it. That's fine. The other thing is that everything is you can see all the terms are given in terms of per minute or per minute squared, and time is given in minutes. So if time was given in, let's say, hours, then I would convert it to minutes so that everything all the terms are in the same units. So the bottom line is, if you have an equal sign, you are not really calculating a quantity from a formula, but you have an equation like this, then in this case, you can use other units like these, in this case, min. As long as all the terms, they have the same units. For example, for acceleration, if you have radians per minute squared, then I would convert it to rev. Or what I could do is I could just leave this as radians, and I could convert revs to radians. So it's up to you as long as you are consistent in the equation. So if you do the calculations, the answer turns out to be -50 RPM. So initially it was rotating counterclockwise with 300 RPM. So what happened? What happened is in 7 minutes, remember there is an acceleration in clockwise direction. That means there's a force in the clockwise direction. So see the velocity, angular speed, and the force there in the opposite direction. So this force will actually stop it, right? So it will stop it first, and then it will start rotating it in the counterclockwise direction, which is negative. So if you wait for 7 minutes, it turns out that its direction changes and it now moves with final speed, which is 50 RPM in the clockwise direction. And that's this negative sign is the reason, or it tells us that this is rotating now in clockwise direction. Okay, so we will now, so we talked about angular speed, okay? So angular speed was about rotation of the object as a whole. So if you have a merry-go-round like this, so angular speed tells us the whole object rotates with that speed, angular speed. But we can also talk about tangential or linear speed of certain points on that object. For example, so there are two kids. One of them is at this point, the other is close to the rim at this point, or let's call it this point. So we can talk about their linear velocities. Both have angular velocity omega, but their linear velocities will be different. Linear velocity, so these are the same things. Sometimes it's called tangential velocity or linear speed or linear velocity. It's shown either by v or vt for tangential. So it's nothing but our good old linear speed. So linear speed is, if you remember, it's delta x dy by delta t. And let's think about this. Let's imagine this situation where these kids, they make one full rotation. So what is the distance for one full rotation? Let's consider this one, child 2. So he makes one full rotation. Okay. Now that distance is, if this is r, that distance will be 2 pi r, right? It's the circumference. And what would be the time for that? Well, that time is, it's period, because we're talking about one motion, one full motion, and it's period by definition. And if you remember the definition of the period, it was t equals 2 pi divided by omega. And if you just flip this, and 2 pi's cancel, and flip omega, you will get omega times r. So the tangential velocity is then, or the linear velocity, it depends on the angular speed and also the radius. So that means if the radius is more, then the tangential speed or the linear speed is more. In fact, if you are sitting here, the radius is 0, so you would not experience any linear speed. But if you are getting close to the rim, the velocity of the kid, that the velocity that the child feels or experiences, it's getting more and more. In fact, at the rim, at this point, the tangential speed is the maximum because you get the maximum radius or the maximum distance from the axis of rotation. So angular speed, omega, doesn't depend on r, it doesn't depend on radius, as it's in units of radians per time. See, there's really no distance in this unit. It's basically degrees, radians, divided by time. So it could be radians per second, radians per minute. There's really no distance. So omega doesn't depend on r. But the tangential or linear speed, it depends on the radius. By definition here, you can see that. It depends on radius. So it's minimum, which is 0, at the center of the rotation, and maximum at the rim. So at the center, it's 0, and at the rim, it's maximum, because radius is maximum at the rim. So if you remember, we defined arc length, which was this distance, as r times omega. And I emphasize that we have to use radians in this formula for theta, not revs or degrees for this formula. Now, if you use this tangential or linear speed formula, which we derived in the previous slide, then in this case, what you should use is, again, either radians per second, radians per minute, radians per hour. So the denominator can be any time unit, but for the numerator, you have to use radians. So here, V equals tangential or linear speed, angular speed times radius. Now, if you look at the units or the dimensions, so this is, let's call it meter per second. It could be kilometers per hour, anything, but let's call it meter per second for this example. So this one is meters. Now, you could say, well, if this is meter per second, there's an equal sign. If this is meters, then there should be 1 over seconds, but that's not correct. There is also another unit here, which is radian. So it's not easy to see it from here, but always keep in mind in these formulas, there is radian here. Okay, here's an example. If this car is rotating around on this, going around on this 2 kilometers radius circle with the speed 60 kilometers per hour. So this is the tangential or linear speed, and that's the speed that the driver would see on the odometer. So he or she would see 60 kilometers per hour. So that's tangential linear speed. Again, the odometer gives you the tangential or linear speed, same thing. But if you want to calculate the angular speed, it depends on the radius. So even though you always see 60, if you are going around a circle of which radius is 2 kilometers, then it will be 60 divided by 2. So I'm using it, not converting it to meters, because speed is already in kilometers per hour. So if you do this calculation, so it will be 60 divided by 2. This should be 30 radians per, not seconds, but hour. So it should be radians per hour. So if the radius was 4 kilometers, then this would be 60 divided by 4. So it will be 15 radians per hour. So as you can see here, the linear speed is fixed. Then because we put r on the other side, it looks like the angular speed also depends on the radius. So you find different angular speed for different radius. But this, don't confuse what I said, this one with with what I said in the previous slide. In the previous slide, what I said is, for a given, so let's say you have an object, let's say it's rotating. So for a given angular speed, the tangential speed depends on the radius. So you have different v at different positions. In this case, this is different, even though we are using the same formula. Here, for a fixed, now the difference is we have fixed the linear speed. And of course, if you do that, if you fix linear speed for different radii, you will find different angular speed. You can leave it as radians per hour, or you can convert it to radians per second. So it depends on if you're solving problems in the exam or homeworks, you have to look at the problem question if it's asking for, what units the question is asking for. Now, centripetal acceleration is another acceleration that we will talk about in this chapter. We learned about centripetal acceleration before. If you remember, let's say I was showing you a video of a toy train. So there was this toy train. There was this string that I tied, and I would fix the string at this point with my hand, and the toy train would go in circles. And if you remember, the equation that we wrote for this one is, we would say there is an acceleration towards the center, and we would call that a centripetal. And the cause of that acceleration was the force, the tension force. So we would write F net equals ma, but so F net centripetal equals m times a centripetal. And a centripetal was v squared divided by r. So in this case, for this problem, for t, so instead of F net, we would have t. So the equation would be t equals, because there's no other force, m times v squared divided by r. So centripetal force is there because this train has a velocity in this direction, but when it comes to this point, its velocity is in this direction. Even though the speed doesn't change because the direction changes, there is change in velocity. Remember, velocity is a vector. So when velocity changes, then there is an acceleration, and that acceleration is always towards the center. The other reason why it's towards the center is because the force is always towards the center. So we will still have, again, in this chapter, the centripetal acceleration, and its definition was this one, v squared divided by r, and it's always towards the center. Okay, so if you remember, we derived this formula in the previous slides. Linear velocity is angular velocity times r. The distance from, so this is the distance to the point from the axis of rotation or the center of the object. So instead of v, we're going to write omega r. It's going to be squared, and there's another r here. So one of the r's cancel each other, and we end up with r times omega squared. So this is another way of writing centripetal acceleration. You can write it as in terms of linear velocity, or if you have angular velocity, you can write it this way. Now, there's one more acceleration. So that's called tangential acceleration. And it's, remember, when we use the word tangential, it's just good old linear acceleration. So it's about if this toy or this whole object is accelerating in this linear direction. Okay, or let's say if this is rotating with certain speed, omega, but it can be a constant speed, right? It may not change. In that case, this tangential acceleration will be 0. But if it's accelerating, which means it's, the speed is getting higher or higher, or the speed slowing down, angular speed is getting slower and maybe going to 0. In that case, we would have tangential acceleration. It's change in velocity with respect to time, and v is again omega times r. R is some constant, so it comes out of this delta. So it's r times delta omega divided by delta t, and we had defined this as angular acceleration. So this tangential acceleration becomes r times angular acceleration. So when do we have angular acceleration? Again, if this is constant angular speed, so it's rotating at constant angular speed, in that case, alpha would be 0. So we would not have any tangential acceleration. In other words, this kid would not accelerate in the forward direction because it would be going with the same linear velocity. So we have non-zero alpha if this omega, angular speed, is changing. It could be increasing or decreasing. In that case, we would have non-zero alpha. What about alpha CP, alpha centripetal? Well, alpha centripetal is always there. It doesn't, the object doesn't have to be accelerating. It's actually not related to acceleration. It's related to angular speed. So as long as there's some angular speed, it could be constant, there is always centripetal acceleration, but there's not always angular acceleration. For angular acceleration, you need force that would speed this up or slow it down. Now, finally, because the tangential acceleration is in this direction, which is, the tangent means if you have a circle, these lines are tangents. So this is tangential, the object, this direction. And centripetal acceleration, they have 90 degrees between them. Now, these are vectors. If you are asked, what is the total acceleration? Then you can just do the vectorial addition, and it would give you the total acceleration, which is in this direction. Now, what is total acceleration if there's no angular acceleration? Well, if this term is 0, then this term is 0. So what's left is just ACP, centripetal acceleration. Then the total acceleration will be just centripetal acceleration towards the center. Here, delta V in this equation here is a change in tangential linear speed. So if I say speed, understand tangential or linear speed. If I don't say angular speed, if I don't use angular, the word angular, then that means just linear. So delta V is speed, change in speed, not velocity. So it's just a change in the magnitude of velocity or change in speed. Velocity is a vector, so it changes in rotational motion at every moment, as I talked about here. The velocity of the train was changing at every moment, even though the speed may not change, but because the vector is changing, the direction is changing, so we would say the velocity is changing. So speed can be constant or changing. Now let's investigate the constant speed case in the next slide. What happens if this speed is constant, the omega is not changing, and the linear speed v also is not changing? Let's investigate that situation. So rotation with constant speed. Again, if I don't say angular, that means linear speed. Okay. So we have this object. Let's say it's rotating around its center. So let's take a snapshot, take a picture of that object at different times. Let's say initially we take a picture of this point. Let's say we are interested in this cross. So that cross is here, and we see that its velocity is to the right, and its final velocity, and then we take another snapshot after some time. Now its velocity is pointing down in this direction. And let's say the speed is not changing because we said constant speed, so the speed will not changing. Only the direction is changing. Now, what is delta V? Well, delta V is change in, this is again speed, not velocity. See, there's no vector sign. So final speed minus initial speed. Final speed is V, initial speed is V, and the difference is 0. Now, if you calculate AT, which is the tangential acceleration, which means the acceleration in, the change in this speed, which is delta V, which is in this case 0, divided by delta T, and we find 0. Now, note that there's no vector sign here, so V's in these formulas, they are not velocities. Hence, this is a scalar subtraction, not vectorial. So angular acceleration alpha is related to change in angular speed. So alpha, these Greek letters, when we talk about Greek letters, they are angular. Okay, for angular stuff, we use Greek letters. So alpha is its change in angular speed. So alpha equals delta omega divided by delta t. If the disk rotates with constant angular speed, there's no alpha. So that's, in fact, this is the situation. So it rotates with constant speed, and it also corresponds to constant angular speed in this case. So there's no alpha, there's no angular acceleration, hence there's no tangential acceleration as well. Because if you remember from the formula, alpha and tangential acceleration, they are related. So if this is 0, then tangential is also 0. But even at constant angular speed, if we have constant angular speed, the centripetal acceleration is non-zero, because this did not depend on, it only depends on omega. It did not depend on alpha. So even if alpha is 0, because omega is not 0, there is always centripetal acceleration. That's related to the vector nature of velocity, and direction of the velocity changes in rotational motion. As I talked about the example of train, now if you want to calculate centripetal acceleration, now you don't look at the scalars, but you do the vectoral subtraction. If you remember from the earlier chapters, then you will find non-zero centripetal acceleration. So even if there is no acceleration, the bottom line is, if this is not 0, if you have even constant, you have non-zero centripetal acceleration. But if this is constant, then alpha would be 0. So alpha is the acceleration that changes this omega. Now, we can talk about these linear quantities like the centripetal acceleration or tangential acceleration. We can talk about for different points. So we can talk about this point. We can talk about this point. So let's take this purple child here. So for this point, the angular speed is counterclockwise. And if the acceleration is also counterclockwise, angular acceleration, then we would have tangential acceleration in this direction because it's even accelerating. And so the angular speed is increasing. And we always have the centripetal acceleration towards the center. So the total, if you do the vectorial sum, so you have to sum these up, these two accelerations vectorially, so it will be in this direction. If again, there is some counterclockwise rotation with constant speed, constant angular speed, and let's say if the angular acceleration is 0, again, centripetal acceleration will be there because now look at it, it doesn't depend on alpha, even though alpha is here 0, it's not 0. But the tangential acceleration, because it depends on alpha, now because alpha is 0 in this case, then we would not have any tangential acceleration in this direction. So the total acceleration basically becomes the centripetal acceleration. Now the last cases, we have again counterclockwise rotation. Now we have the centripetal acceleration as usual towards the center. But if it's slowing down, which means we have negative, we have acceleration in the opposite direction to the, not necessarily negative, but in this case, because the rotation is in clockwise, if it's slowing down, then the acceleration should be counterclockwise, angular acceleration. And the tangential acceleration depends on the angular acceleration. So tangential would be now in this way. Remember, this is still rotating counterclockwise. And in this case, if you vectorially sum these up, this vector and this vector, you will get the total acceleration in this direction. So what does that mean? For example, what is the meaning of total acceleration? So now because there is rotational motion, and that gives you ACP, and because there is a possibility of accelerating, so in this case, let's say this thing is accelerating, so the omega is increasing in this case. So this child will feel like he or she is accelerating somehow in this direction. It's a combination of these two accelerations. In this slide, we have a summary of the concepts that we learned. So I know there are a lot of different accelerations and velocities, but this summarizes all. So the radius independent angular quantities. So the angular quantities are radius independent. That means there's no R term in these formulas. They are about the rotation of the whole object as a whole. So this whole object is rotating with certain angular velocity, or maybe even it's accelerating in the angular direction. So it may have angular acceleration as well, but they are, as you can see, they don't depend on R, so it's not necessarily different for, they're not different for different points on this disk. So they're the same for all points. And the formula for angular velocity depends on the change in angle per time, or you can rewrite it as 2 pi divided by period. And the acceleration is basically the change of angular velocity with respect to time. So the other variables they are radius dependent, and they are linear quantities, and they're about a point. They're about a point on a rotating object at a distance r from the axis of rotation. So in this example, in this figure, our point is the ladybug, and we will discuss its linear quantities, like the linear, or it's also called tangential speed or tangential acceleration. So the distance r that you will see in these formulas, it's not necessarily the distance between the object and the center of the object. In this case, this disk is rotating around its center, but you could, in general, you can have a amorphous object like this. For example, it can rotate around this axis. So in this case, you should take r as the distance from that axis of rotation to the point. Okay, so for linear velocity, we can show it with v or vt. T is for tangential, the same thing. It's basically the change of position divided by time. You can write it as 2 pi r, because if you think about the whole circumference of this path and the time that it takes for making one full rotation, which is period, and you can rewrite this part as omega, and you can rewrite this delta x divided by delta t as omega r. So this tangential speed is the momentary, instantaneous speed of this ladybug in this direction. So this ladybug is not, it's stationary with respect to this disk. So it's not walking, it's just stationary with respect to the disk. But because the whole disk is rotating, this ladybug will feel some velocity in this direction. Of course, when the ladybug comes here, it will feel the rotation in this direction, and when it's here, the velocity in this direction. Here, the velocity, the linear velocity it will be in this direction. But for a given instant, it will feel some linear velocity. Now, if you ask this ladybug, is your velocity changing? Now, of course, the direction is changing, but you can ask this question: if is your speed changing? Okay, the linear speed. If the ladybug says yes, then that means there is tangential acceleration. So the point here is tangential acceleration can be 0, and you can actually see it from here. If angular acceleration, which is here, is 0. When is it 0? When the angular speed, when the change of angular speed with respect to time is 0, that means this is rotating with constant angular speed. So that angular speed is not changing. In that case, alpha is 0. Then alpha tangential, A tangential is also 0. What does that mean? This is going to this is going to rotate with constant angular speed. That also means there will be no tangential acceleration. And this ladybug will tell you that its linear speed, it has some linear speed, and it's not changing. It will tell you that its linear speed is not changing. What happens when you have angular acceleration? It could be positive or negative. If it's positive, this ladybug will tell you, let's say initially the speed is this much, and maybe the speed becomes like this, and maybe even more. That means there's a positive angular acceleration, so that gives you positive tangential acceleration. So this ladybug will tell you that the linear speed is increasing. Or we can have negative angular acceleration. In that case, the linear speed will decrease. So initially it's this much, and then it will be this much, and then it will be even smaller, and maybe at this point it will stop. So these quantities, the linear quantities, are the quantities that this ladybug is feeling. The velocity or acceleration. And we can also talk about centripetal acceleration. Now look at the formula for it. It doesn't depend on angular acceleration. So even if there's constant speed, then there's angular acceleration. So we can say this, so as we talked about it, this depends on alpha. So if there's no acceleration in the radial direction, then if you have like a constant omega, then this term will be 0. But centripetal acceleration is always there if there's any rotational motion. Because it doesn't depend on acceleration, it depends on angular velocity or angular speed. So anytime there is an angular motion, like rotation, there will be always centripetal acceleration. So centripetal acceleration is related to the fact that this bug, because of its inertia, if this wheel or disc turns, normally it would want to go in this direction, right? So the ladybug should be somewhere here. Okay, but something pulled it in. So instead of being up here, ladybug is actually here. Why so? What is the force that pulls the ladybug in all the time? That force is coming from the friction between the ladybug and the disk. And that force and the mass of the ladybug, they will create this centripetal acceleration. So if you want to write the equation, friction would be equal to m of ladybug, let me call it L, times ACP. And that ACP, you can write it as either v squared divided by r, or you can also write it as r times omega squared. These are the same thing. And this force is the source of the centripetal acceleration. We talked about this when we, I think it was in chapter 6, I showed you a video with the toy train. So we had a toy train and there was some string connected, and I was fixing this string at some point with my finger, and the toy train would make a circular motion. So the toy train normally wants to go here, but because of this string, it actually ends up here. Why so? Because the force is always, there's a force always pulling the train in, and that force is actually the tension force. And when the object moves in, that means there's an acceleration towards radially inward to the center, and that acceleration is again the centripetal acceleration. Okay, finally this a total acceleration, it's basically just the addition of tangential acceleration and the centripetal acceleration. So the overall feeling, if you ask this ladybug, what do you feel about your acceleration? It will tell you that it feels like it's accelerating in this direction. Of course, if AT is much larger than ACP, then it will be more like in this direction. If ACP is larger than AT, it will be more like in this direction. And if AT is completely zero, which means there's no angular acceleration, then A total will be equal to ACP. So that's the total linear acceleration. So you have to spend some time with the slide. I know there are just a lot of concepts and different definitions, but you will get used to them. So one application of this is the centrifuge. When you give a blood in a medical center, what they want is actually they want to separate the plasma in your blood and erythrocytes so that they can do the tests and analysis. But when they take a blood, it's basically initially it's homogeneous, right? These are not separated. If they wait for the blood to precipitate, that means the erythrocytes going down and plasma is staying up because it has less density. It will take days. For this process, it will take days, but they don't have days. So they put these tubes into a centrifuge that rotates and accelerates really fast in either clockwise or counterclockwise. So what happens is it's actually like the bus. If this bus or any vehicle, if it's rotating to the left, what happens? if it's rotating really, really fast to the left, turning left, then all the passengers would actually collect on this side, right? Because of the effect of the inertia. All the passengers will collect on this side. So the same thing happens here. Because of this rotation, all these erythrocytes, they're collecting down here. Well, they would collect there anyways by the effect of gravity if you wait several days, but this makes the process really, really fast. So instead of g, they feel acceleration as large as 13,000 g. So if it takes days for the blood cells to precipitate, it means go down to the bottom of the tube under the influence of gravity g, which is 9.8, it takes minutes with the centrifuge, this device, since the effective gravity is like 13,000 g. When the gravity is much, much larger than g, of course, this precipitation becomes much, much easier. Of course, there's no large planet or star to give you this much acceleration. You get that acceleration by using this rotational motion. So it's an effective gravity. It's not really gravity, but it looks like a huge gravity effect. Now we move to rolling motion. So before we talked about objects rotating and they were fixed in that space point. So they were not really moving to the left or up, down. They were just rotating at the same place. Now, what we will have here, we will have like vehicles, bicycle tires, bicycle wheels, car tires. You know, they are rotating and they're also moving in certain directions, right? So now, in general, an object may be rotating at the same place. Let's think about this car tire. Okay, we have car tires. So they may be rotating here, okay? But if the ground is icy or snowy, then they will rotate. So they will have some angular velocity, but the car will not move because, you know, it's slippery on the ground. So that's possible. Or the tires maybe you can push the brakes. So you push on the brakes, the tires are locked because of the brakes, okay? So the angular velocity of the tires is 0, but because the car is maybe it's sliding or slipping, it can have some center of mass velocity. So in general, the point here is in general you can have in general the angular velocity of the tires and the center of mass velocity of the tires, like as a whole, translational or linear motion, they are independent. But in normal motion, where you drive your car or your bicycle, ride your bicycle, there's one condition that's satisfied, and that's called rolling without slipping. Here, there's slipping. Here, there's slipping. But if you have this condition satisfied, rolling without slipping, that's very important, then there's a relationship between this center of mass or linear or translational speed as a whole and the angular speed of the tires. Now, what is that relation? We are going to find it here. Now, imagine that this tire, or let's say bicycle wheel, is rotating and coming here. And I want it to make one full rotation. So see this yellow point? So it will rotate and come back to this top point. So it makes one full rotation. And I'm going to use this equation. So it will be x equals, actually, let's say cm. So what is the distance? Well, the distance that it will take will be, just because it makes one full rotation, it will be 2 pi r, right? The circumference of this thing, this bicycle wheel. So 2 pi r is x. And VCM, we're going to calculate what it is. And what is the time that it takes for one full rotation? Well, it's the period. So VCM equals 2 pi r divided by period, which is here. Now, I'm going to separate this term here, And you know that we define this to be omega, which is the angular speed. So then you can write VCM, the center of mass motion of the wheel. It means like the motion of the wheel in this forward direction. So it's not related to rotation. It's basically, it's the motion or it's the speed of the wheel that's relevant to translational motion. So basically translation means going from one place to other place. So as I said before, up here, these two are in general independent, but if this condition is satisfied, then we have VCM equals omega r. So this motion, center of mass motion, motion of the whole thing, the translational, is related to the rotational motion of the wheel when this condition is satisfied, rolling without slipping. So this thing is not slipping. If it's not slipping, then we have this condition. We will use this condition a lot in the following slides. Okay, for example, we are going to talk about cartwheel here. Cartwheel is this making this motion. Now, in the next slide, I will show you wheels, like the velocities, linear velocities, or the total velocities at different points of the wheel. But before that, let me show you, let me explain it over cartwheel because it's more transparent. It's easier to understand here, and then we will go to the wheels. So rolling without slipping, it's basically, as we described, if you think about this point, when this wheel rotates, this point also moves. So that means rolling without slipping. So it's rolling and going forward at the same time, and during this motion, there's no slipping. So this motion, you can see that there is rotation. So there's angular speed, but there's also translation. Translation means going from one place to another place in the linear direction. So there's also VCM. So this whole motion, rolling without slipping, we can divide it into two as the pure rotation, which is related to omega, pure rotation, and pure translation, which is related to VCM. Okay, now the question is, if we sum these up, if we add these velocities that are coming from these, then what will be the velocities of this person doing cartwheel at different points of her body? So now we are talking about total speeds, which is combination of the rotation and translation. Now the total speed of this person, so first of all, this person is not rotating around the center of mass or the middle point. It's rotating around this point, the ground, right? And you can see it here. The rotation axis is actually here. Now, during the cartwheel, what is the velocity of the hands? Well, because they are not slipping, they are at the same place instantaneously, they have zero velocity. At the middle point, velocity is omega r, and at the top point, which is the tip of the legs, the velocity is twice as large as the middle point. And in fact, you can see it here. Now look at the hands. Momentarily, they are stationary. And look at the belly. It moves with certain speed. And look at the legs. They have much more speed than the belly. So this happens, we get these numbers because we combined pure rotation, the speed coming from the rotation and the speed coming from the translation. Now, let's prove that's true. These numbers are true in the next slide. So we said rolling without slipping is pure rotation plus pure translation. So pure rotation at any point in the wheel, it creates the tangential velocity, right? It has tangential velocity at different points. And we learned that it was r times omega, tangential velocity. It's the definition of the tangential velocity. And at every point, it's r times omega if you are at a distance from the center r. So we can think of this thing as rotating around the center. So we are just talking about pure rotation here, not translation. So these points would have these velocities. So if you were a small person sitting on this point, you would feel this much velocity in the linear direction. Now, what about the translation? Well, translation, now we are considering pure translation, no rotation here, and then we will combine them. So translation means if rolling without slipping is satisfied, then the VCM, center of mass motion as a whole, it's also equal to r times omega. V tangential and VCM, they're different. They are different concepts. So tangential velocity is the velocity of any point that's from the distance from the center. So that's tangential velocity, and it's coming from the rotation. But center of mass motion is the motion in the forward direction. So it's the translational motion. But because rolling without slipping condition is satisfied here, the problem says it's not slipping, okay, then we also have VCM equal to r omega. Now that VCM is the same everywhere, and it's to the right, because this object, this wheel, is moving to the right forward with velocity VCM, and it's omega r. And every object, every point, every part of this bicycle wheel is moving with the same VCM in the forward direction. Now we are going to combine them. Basically, we're going to combine at any point. At the top point, we will add velocities. At the bottom point, we will add velocity. And also at the middle point, we will add the velocity contributions coming from both rotation and translation. Now, let's start with the top. So at the top point, there is velocity, r omega, coming from tangential velocity, which is coming from rotation. And there is another velocity, which is coming from translation. And both are r omega. So when you add them up, you get 2r omega. In the middle point, the rotation doesn't contribute, but the translational motion contributes r omega. So you get just the total is r omega. These are all total. So total velocity. Total means rotation plus translation. Okay, now look at the bottom point. At the bottom point, the velocity contribution from the rotation is to the left, r omega, and the translational contribution to the velocity is again r omega, but it's in the forward direction. Now these are two vectors. They have the same magnitude, but they're in opposite directions. What happens when you add them up? Well, you get 0. So this point has 0 velocity. Now you can say when this wheel comes here, that point goes up, then it has velocity. That's correct. But what we are discussing here is the instantaneous velocities. So that means in a given time, you can think of it as a really small time. The velocities at this point is 0. The velocities at this point is r omega. And the velocity at the top point is 2r omega. So if you're a small person sitting here, you would say your velocity, the total velocity, is 2r omega. And if you're sitting here, you would say it's r omega. And if you are here, then you would say instantaneously, the velocity would be, you would feel 0. Let me go back to the previous slide. And now look at, again, the hands, the velocity is 0, the total. Remember, it has two contributions, one from rotation, coming from rotation, the other coming from linear motion, translational motion. The belly point, the middle point, moves with certain speed. And the legs, top point, moves really faster than the middle point. Okay, here's an example. A car with tires of radius 31 centimeters drives on a highway at 65 miles per hour. What is the angular speed of the tires? Well, we just use this formula, V equals omega R. Okay, so this is VCM, right? This is the translational motion, speed of translational motion. So if this is normal motion, then rolling without slipping condition is satisfied. So from here, you can calculate angular speed of the tires. So this is VCM. So VCM is given to be 65 miles per hour. And you divide it by R, which is converted to meters. Now, if you want the answer in radians per second, first you have to convert this hour to second. And you have to convert this miles to meters so that mile and meters cancel each other, so that what's left would be just meter per 1 over seconds. So for that conversion, if you multiply 65 miles per hour with this number, you will get meter per second because these miles per hour, they will cancel. And where do you get this number? Well, you just convert 1 miles per hour. So this is like miles per hour converted to meter per second, and you get this relation. Now, if you rewrite it as, let's put miles per hour to the denominator here. So what you would get is 1 equals 0.447 meter per second divided by 1 miles per hour. So this whole thing is 1. So you can multiply any number with 1, right? If I multiply this 65 miles per hour with 1, it will not change anything. So I can do that. And 1, instead of 1, I can also write this whole thing. And this will help me convert miles per hour to meter per second. And this is, of course, this is angular. So you have to write, also you have to add the radians. Even though it's not seen here, you have to add radians by hand. But 1 over second is coming from here because these meters will also cancel. So what's left here is 1 over seconds. So 94 radians. Now, if you think about it, 2 pi is about 6.28, right? So 2 pi radians is about 6.28 radians, same thing. And this is how many revolutions? This is like 1 rev, because 1 rev is 2 pi, 1 full motion. So if you divide this number, 94, by 6.28, it makes approximately 15 revolutions per second. So you can also rewrite it as it's approximately 15 rev per second, if you want to convert it. Now, the second part of the question is, what is the linear speed? Here, it means the total. Total includes the contribution from the rotation and the translation. What is the linear speed of the tops of the tire? So what is the speed of the point at the top of the tire? Well, we learned that it would be 2 times r omega, and we know r omega is VCM equals r omega. So this is basically 2 VCM. So if VCM is 65 miles per hour, then this will be just multiplied by 2, 130 miles per hour. Okay, now we defined angular velocity in other concepts, so we can move to kinetic energy now. Let's say we have an object like this. It's rotating, it's following this circular path, rotating around some center, and that distance is r. So the question is, what is the kinetic energy of this object, which is coming from the rotation? So there's no translation here, it's pure rotation. What is the kinetic energy? Well, we can start from 1/2 mv squared, which is true for the linear case. Now, instead of v, we are going to write, so you can treat this as tangential velocity, or the linear velocity, and the definition of tangential velocity is r omega. Now, what we're going to do is, so we're going to write m r squared together here, and separate the omega squared here. And we will call this term I, which is called angular mass, rotational mass, or moment of inertia. This we will use in this lecture. We will prefer this term, moment of inertia. It's the most common term for this one. So now it looks like the kinetic energy due to rotation, it looks like the linear kinetic energy, except so instead of linear speed, we have angular speed. But instead of m, now we have a new definition, which is I, which is moment of inertia. Now, what is it? Well, we can understand it this way. Mass is, if you think about it, it's the resistance to linear movement. The higher the mass, the harder to accelerate it. Right? If you think about F equals ma, so if m is large for a given force, if m is large, then a is small. So larger mass means it's harder to accelerate it, it's harder to move it. So we can define mass or inertia as the resistance to linear movement. Now, moment of inertia is just like mass, but it's resistance to rotational movement. So if I is large, so let's say we have a disk or any other object. So let's say this is the axis of rotation, and we want to rotate it in this way with certain angular speed. If I of this disk is large, that means it will be harder and harder to rotate it in clockwise or counterclockwise direction. If I is small, then it will be easier to rotate it. It's like if you have a door which has more mass, it's harder to rotate it, it's harder to open it, right? But the lighter door, it's easier to open or close it. But the thing here is, you have to notice, it doesn't only depend on m, it also depends on r. And in the following slides, we will see what that r is. If you have a point-like object like this, it's a point. It's basically r is the distance from the object to the axis of rotation here, this point. But if you have an object, a solid object like this, of course, here, there's not just one point, but there are many point masses everywhere. And we will see in the following slides what that r will be. Here's another example to understand moment of inertia better. So if you have a stick like this, and you can break it into two, and you can glue those two parts, so it will still have the same mass. Now, the upper one, it has more extent, it's longer. So that means if you look at this formula, it will have larger moment of inertia, so it will be harder to rotate this one. Now, the second one, although it has the same mass, it's actually the same stick. It's just cut into half and glued together like this. So, but just because it has small extent, it's shorter, it will have smaller moment of inertia. So this one is easier to rotate. So moment of inertia is not only related to mass, it's also related to the extent, how wide or how long the object is. So let's continue with point masses, and then we will move to objects which are not point masses, but solid objects. But here, we have, so these rods are massless. So we will deal with point objects, point masses. So in this case, there are 3. And what happens if you have more than one mass? If there are multiple masses, calculating the moment of inertia by summation of moment of inertia of each mass. So you have to basically do m1 r1 squared plus m2 r2 squared plus m3 r3 squared. Now what is this r? It's the perpendicular distance of the mass to the axis of rotation. So let's start with this one. So we will write m times r squared for all terms. So this one is fixed from, so this is the axis of rotation. You can think of this as on the ground, and you fix it from this point, you nail it to the ground, and it can rotate clockwise or counterclockwise or clockwise on the ground. Okay, so now so let's start with this mass. So 1.2, mass is 1.2, and write the distance to the axis of rotation. It's 2. Of course, you have to take the square because of the formula. Now for this mass, 2.5, I'm not really writing it because the distance from mass to the axis of rotation is 0 because it's already here. Now for the third one, 9 kilogram. Now the distance from the mass to the axis of rotation is this distance. If this is 1, if this is 2, that distance r would be 1 squared plus 2 squared. So r is square root 5. And because we will take the square of it, so it will be actually the square root 5, 5 squared, square root 5 squared, it will be 5. If you do the multiplications and the summation, you will find the moment of inertia is for this object rotating around this axis of rotation is 49.8 kilogram meter squared. Now, take the same object, now rotate it around this axis. Okay, so that axis is going through this mass now. So now it rotates like this. So it goes into the page like this. So it rotates like this and comes out of the page and goes into the page. Now the distance from 1.2 mass to, again, the axis of rotation is 2. For this one, again, there's no distance, 0. Now for this 9 kilogram object, the distance to the axis of rotation, you have to take the perpendicular distance, or you can think of it as the shortest distance. The shortest distance is this one. This is the perpendicular distance to the axis of rotation. Here we again took the perpendicular distance, as you can see. So this distance is just 2. So in this case, I will have 2 squared. And if you calculate it, it's 40.8 kilogram meters squared. Now this one is smaller. Now we have the same object, but the moment of inertia, the resistance to rotation, depends on around which axis you are rotating it. So this one is easier, so that it's smaller number, so that means this one is easier to rotate. This one is a little bit harder to rotate in comparison to the other one. Okay, so there's an important point here. There's no effect of gravity in the calculation of moment of inertia. We did not talk about G. Okay, so the hardness of rotating an object is due to the mass and the radius, and not gravity. And you can also see that this is m/r squared. There's no gravity term. And that hardness is coming from hardness to, or the resistance to rotation comes from the masses. because the masses don't like to be moved linearly or in the rotational direction, in the angular direction, and that's related to inertia. Okay, let's calculate the total kinetic energy of this system now. We have two objects. Again, these the rods that are connecting these objects are massless, so we will just take these 2 point-like objects. And we will use this formula. Now, for the small object here, its kinetic energy will be 1/2. Now, this is I, right? And I is mr squared, you know, from the formula. And for the second one, we will write 1/2. We'll write 2m is the mass, and 2r squared is the distance. So this whole thing is now I. You can write I2, I1. So this term brings 1 mr squared. This term brings 2 squared 4, 8. So this brings 8. So 1 plus 8 is 9. And there are the 1/2. So 9/2 mr squared omega squared. So here we calculated the kinetic energies separately. The other option is you calculate the total. So how do you calculate it? I total equals, for this one, it will be mr squared. For the second one, it will be 2m 2r squared. So this is 8 and it's 9. So 9mr squared. And then you can write just one kinetic energy, 1/2, because they're rotating with the same angular speed. I don't have to write different angular speeds, just one. And for I can write this one, 9m squared, mr squared, and you find the same result here. So the point here is either you can calculate the total moment of inertia of the system and write the kinetic energy, or you can write the kinetic energy separately. But again, we are using the same omega for both objects because they are both rotating with the same omega. Now there's this caution: if you use radian per second, you have to use radians per second for omega, angular speed, if you want to find energy in units of joule. So both are SI units. So in the previous examples, we solved when you had equation. Let's say you have, final angular speed equals initial angular speed plus acceleration times t. Now, if you use, for example, radians per minute for all of them, and for the time, if you use minute, for acceleration radians per minute squared, and for these ones, radians per minute, then that's fine, because whatever, as long as you're consistent, whatever units you will use, at the end of the day, they will cancel each other. Or if you use minutes for everything, here, if you use minutes, your result will be in terms of 1/minutes. So if you use 1/minutes, your result will be 1/minutes. This is true for equations, but if you calculate some formula, and if you go from a certain units to another newly defined units like joules, then you have to use SI units for each term. For this one, you have to use radians per second. For moment of inertia, you have to use kilogram meter squared. And if you do that, you will find joules. And that's the SI, that's the standard unit for energy. Now, what happens if in this formula, let's say if you use radians per minute or revolutions per second? Well, again, you will find some number, you will find energy, but that energy unit will be not joules. For example, let's say we use kilogram meter squared. And for this one, let's say we use revolutions per minute. Okay, so you will calculate energy, but that energy will be in these units, not in joules. Because joules is equal to kilogram meter squared radians per seconds. Only if you get these units right, you can call this whole thing as joules. So you have to be careful about this point. Okay, so we talked about the moment of inertia of point particles, but now we are moving into the extended objects, like solid objects, like these ones. So moment of inertia of various regular objects of the same mass m. So let's say they have the same mass, same radius, these two objects, but this is a hoop or cylindrical shell, the same thing. This is a disk or a solid cylinder. Solid means the inside is filled. Okay, and if you look at their moment of inertia, even though they have the same radius and same mass, their moment of inertia is different. The difference is coming from the fact that most of the mass in the case of the hoop is collected around the rim, but in the case of the disk, only some part of the mass is outside, but inside there is also mass distribution. So this has, you can think of the masses here has more extent, more radius. Here, some masses, they have 0 radius, some have some certain r divided by 2 or different r's, and some, only a few of the mass particles, they have radius r. So this has most of the mass because, in fact, all of the mass, because here they have extent or radius r. This moment of inertia is larger than this one. So what does that mean? What happens if moment of inertia is greater? Then it means, if you remember, it's harder to turn it. So it's harder to turn a hoop than a disk, given that they have the same mass. Of course, if masses are different, r's are different, then i's will be different. So we are comparing the case where the mass is the same, r is the same for these two objects. Now what happens to the moment of inertia? Well, just because of the geometry, just because of the mass distribution, you get these different prefactors. Okay, so we have a collection of objects and their moment of inertia are given. In a calculus-based physics class, you also calculate these numbers. So you calculate, these prefactors, all of them. But because this is an algebra-based physics class, you will be given these numbers in the formula sheet. So you don't have to. So you won't have to calculate these numbers. So you will be given. But in principle, you can calculate these moment of inertia by taking integral of the density of these objects with respect to their also using their shape. Okay, so in this class, these will be given. For the hoop or cylindrical shell, the same thing. So if you have a cylindrical shell like this, it can be longer, doesn't matter. As you can see, this length is not part of the moment of inertia. So it only depends on the radius and mass. So this part is empty. It's only shell. So you would use in that case this one. If you have a disk or solid cylinder, now if you can also have a solid cylinder, so inside could be filled. In this case, you would use this one with the 1/2. Now, this is the same object with this one, disk again, or a solid cylinder, but it's now rotating around its rim. Now, the axis of rotation is passing through its rim. In that case, you would use 3/2 mr². Here, r is the total radius. So it's the radius of the object. It's not a variable, it's the radius of the object. For a long, thin rod, and if it's rotated around its middle point, then you use 1/12 ml². If it's rotating around one of its ends, then you would use 1 1 over 3 ml squared. Now, if you have a hollow sphere, hollow means this is a shell, inside is empty. Inside is empty, then you would use 2 divided by 3 mr squared. If it's a solid, solid means inside is filled. Then you would use this one. And if you rotate the solid sphere around its rim, then you would use this number. For a solid plate, it's like a book. And if you rotate it around this axis, so in plane of plate, it will be 1/12. But if you rotate it around this middle point, then it will be again 1/12, but you would also have to add this another dimension. So L is this dimension and W is this dimension. Okay, now we can talk about the total kinetic energy of an object that has both rotational motion and translational motion. The total kinetic energy of a rolling object is the sum of its kinetic energies from linear center of mass, this is translational, and rotational motions. So linear motion, we learned this when we did linear motion, it's 1/2 mv squared. Here we are using cm, center of mass. That means this wheel goes from here, here, so that's a translational motion, linear motion. And it also undergoes rotational motion with angular speed, and that part contributes this 1/2 times moment of inertia times angular speed squared. So that is the kinetic energy coming from pure rotation. Now in general, these two, VCM and omega, they are independent. We talked about the examples. For example, if you have a car tire that's rotating, so let's say it's rotating in the snow this way with some angular speed, but because it's in the snow, maybe it's stuck, maybe it's not moving forward, so VCM could be 0. You can see that in general, there's no relationship between them. So you have to write down these two separate terms. But if it rolls without slipping, so that's basically the normal motion of most of the, the cars or bicycles or any vehicle. If there's no slipping, if the ground is not icy or there's no snow, then we also have this condition. Now what happens? So we have this condition, but keep in mind this doesn't have to be true always, as we saw here in this example, even though it's very common in nature. But what happens if you have this relation? Well, what happens is, now instead of VCM, you can write omega r squared here. So everything will be in terms of omega, or instead of omega, you can write VCM divided by r squared. So everything then will be in terms of VCM. So you can reduce it to one variable. An object in general could have any translational speed and angular speed independent from each other. So these two are in general independent from each other. For example, on a snowy ground, the car tire may rotate, so you would have non-zero angular speed, but the car may not move forward. So translational speed could be 0. Okay, here's a question. Now we have a short video and I will play it, but let's read the question first. We have the metal hoop and the wooden disc. So we have two discs here. One of them is metal, the other is wood, but it doesn't matter. The material doesn't matter. They have the same mass, and they have the same radius r. So now the question is, which one will win the race if they both are rolling without slipping? So this condition is satisfied. So now when you release this, this block, so they start from the same height, same point, and they will come down. The question is, which one will come down first? Okay, let's play the video and see what happens.
Let's see which one that is.
As you can see, the disk comes down before the hoop. So the disk is winning this race. Now, why is that happening? Let's do the math and prove, in fact, the disk is winning the race. So, which object will win the race if they both are rolling without slipping, both have the same mass and the same radius? Here's the solution. So both will have the same final total kinetic energy, right, from the linear. So each one will have kinetic energy when they come down here. So kinetic energy of the hoop, and this is kinetic energy of the disk. But they will have rotational parts and the linear parts, both, right? Because they're now rotating, and also they have the translational speed, center of mass speed. Now they will have, these two will be equal to each other. Why? Because both are starting with the same potential energy, and because we assume there's no friction or anything, so they will convert their potential energy into kinetic energy here. And because they start with the same potential energy, they will end up with the same total kinetic energy. So this will have K total, which will be equal to the other one's K total. So these are equal. So, but because K total, it has two parts, right? One is coming from linear motion or translational, the other is rotational. Now, if one of these objects spend more into linear motion, that will have more translational speed at the bottom. That means it will come to the bottom of this incline more quickly. So the one that has more linear part in their kinetic energy will win. Again, the total kinetic energy of both are the same, but one of them has more linear energy, more linear kinetic energy than rotational, so that will come down faster. So we can solve this by basically looking at the ratio of the linear part of the kinetic energy to the rotational part. So let's calculate linear divided by rotational. And I'm going to keep the calculation general, not for specifically for one of these. So the linear part is 1/2 mv VCM squared, and the rotational part is 1/2 I, which is moment of inertia, omega squared. Now, we can write, because rolling without slipping is satisfied, so we can use this relation. So if you substitute here, if you put VCM divided by R instead of omega, so we will have VCM divided by R squared. And let's keep I general, so each one has different I's. At this point, let's keep it general. So VCM squared, they cancel. So what's left is there's M, there's this R squared in here, so it will go up as R squared, and there's I. So this is the ratio. Now, we will use this calculate this ratio for the hoop and the disk. So that ratio for the hoop is, well, m r squared. What is I for the hoop? It's m r squared. So these cancel each other and you find 1. So that means hoop spends 1 unit of energy to linear and 1 unit of energy to rotational. So you can think of it as like 50% of the total energy goes to linear and 50% of the total energy goes to rotational. Now the disk is, if you calculate, so this part is the same, mr squared. Now in the denominator, write the moment of inertia of the disk, 1/2 mr squared. These again cancel. What you find is 2. You can think of this as 2 divided by 1. So it spends 2 units of energy, 2 parts from the total energy into linear, and only 1 part into rotational. So maybe we can say 66% to linear and 33% to rotational. Now you can see that this spends more energy to linear than the hoop. That means it will have more linear energy, which means it will have more translational speed. So if the translational speed of the disk is more, then it will win, it will come down faster than the hoop, so the disk wins. The interpretation of this, so this was the math, but what is the interpretation? Because the moment of inertia of the disk is smaller, if the moment of inertia is smaller, that means it's easier to rotate it, right? So you don't have to spend so much energy to rotation, so that you can use the rest of the energy into linear. So it spends less energy to rotation so that it can use more to linear, so it builds up more translational speed, which helps it to come down quicker. Now, if the previous solution was confusing for you, then you can think of the energy conservation. So whatever energy they have at the top here, they will have the same energy at the bottom. Okay, so what is the total energy? So for each one, this is so let's write energy initial equals energy final for one object. So I'm not going to write for both of them, not the total, but I will write it for each object. So initial energy is linear kinetic energy, rotational kinetic energy, and the potential energy due to gravity. Now, initially they are stationary, so this term is 0, this term is 0. And the potential energy for any of these is mgh. Now, when one of the objects, it comes down here to the bottom point, the potential energy will be 0 because I put my coordinate system here, y. So this is y equals 0, u equals mgy. Because y is 0, potential energy is 0 here. And from the linear kinetic energy, we have this, which I just write the formula for the rotational. Again, I just write the formula for rotational kinetic energy. Now, keep in mind that I'm just leaving I as general. I'm not putting these numbers or the expressions. So this expression is general. This calculation is general. It works for both the hoop and the disk. So now I have 2 variables here. I want to get rid of them. I can do that because of the rolling without slipping condition. Instead of omega, I can write VCM divided by R, which I do here. Now, everything is in terms of VCM. That's good. And I'm interested in VCM. So whichever has more VCM, it will come down quicker, right? So I'm going to look for the greatest VCM, which one has the greatest VCM. So now here I can rewrite this term here. So the left-hand side is the same. This term is, I can write it as 1/2 m and 1/2 I r squared together. And then I write the common term outside the parentheses. Now, if you want to solve for VCM, what you have to do is you have to take this part, put it in the denominator, and to take the square root of the whole thing, which you end up with this one. So this is VCM. So for these 2 objects, m's are the same, g is of course the same, initial height is the same, r's are the same. Okay, so what's different is just I, because one of them has larger I, the other has half of it. So here I is in the denominator, so whichever has smaller I, that one will have greater VCM. Because if I is small, When you divide a number with a smaller number, overall you get a larger number. So I of the disk is smaller. You can see that it's 1/2 mr squared. So VCM of the disk is greater, which you can see from this equation as well. That's why the disk wins. Now let's move to massive pulleys. So in the previous lectures, we dealt with pulleys, but they were massless. Here it has a mass. The question is, what happens if this M1 drops here and M2 goes up? What is the initial and final energies, and how can you find from the energy conservation the final velocity? How can you relate the final velocities to other variables in this problem? So I'm going to take these bottom points to calculate potential energy. I will take this line as zero potential energy. So initially these are all stationary. So I have to write, so only this has potential energy. There's no other potential energy or kinetic energy. So I will just write M1GH. Now this thing, the M1, it falls down here for a distance h, and of course this M will go up for a distance h, so M now will be here, and they will have some final speed. So we are considering the moment that this hits the ground, but it has not stopped yet. Right that moment, so they will still have the velocities. So in the final case, this doesn't have any potential energy. This has now potential energy M2GH. Be careful about these indices. So this has potential energy. Now both have, because they have velocities, final velocities, we will have kinetic energies for both. Now notice that I'm using the same V final. Why? Well, if these objects are connected with a rope, they should have the same speed and same acceleration. Okay, now is that it? No, we have to, because in this case here, there's another object which is massive. It's the pulley. Does it have any translational energy like 1/2 mv squared? No, because it's fixed here. It doesn't move. Does it have any potential energy? Well, you can write its potential energy like mg this height, but because you will write it in both sides, they will cancel each other. So you don't even have to write it because its height is not changing. Even if you write them, they will just cancel out. Now what's left is the rotational energy. It has, because it's rotating with some angular speed. Initially it was stationary, but now it's rotating with final angular speed. We have to write its rotational kinetic energy. It will be 1/2 I pulley times final angular speed. Now I pulleys, you can look up the list, and for the disk, because it's a disk, it will be 1/2 mr squared. Now so in general, this rotational motion and this V final, the linear motion, they could be different if this rope is slipping. So if there's any bit of slip in the rope around the pulley, then these two velocities, linear and the velocity of the masses or the velocity of the rope and the angular velocity of the pulley, they will be different in general. But if the rope does not slip on the pulley rim, does not slip means this. If the pulley, let's mark this point on the pulley, and let's mark this point on the rope. If this makes some rotation, let's say this point, this mark comes here, and then if there's no slip, the mark on the rope will come exactly at the same point if the rope is not slipping. So if the rope does not slip on the pulley rim, the tangential velocity of the pulley at its rim, so this Vt, tangential speed of the pulley of this point of the pulley, tangential speed of it, will be equal to, so this is the definition, r times omega. That's just coming from the tangential velocity definition. But if there's no slipping, it will be equal to the speed of the rope. And we know that speed of the rope is the same as the speed of the masses, which we call V final in this problem. So from here, what you find is there's a relation, if there's no slipping, there's a relation between V final and omega final. And it's written as this one. So now originally this equation, it had two different variables. They were independent in general. But if this condition is not, if this condition is satisfied, not slipping, then you can use this definition. For example, instead of omega final, we can just write here V final divided by R squared. And that will simplify the equation. Now, instead of two unknowns, we would have just one unknown. Okay, in this example, there is a bowling ball, and without slipping, it rolls. So whenever I see this without slipping, I can write this condition, VCM equals omega. Omega is the angular speed times R is the radius of this object. So the bowling ball, without slipping, rolls up a ramp of height h. Write the energy conservation equation. So we say initial energy, because energy is conserved, initial energy equals final energy. Now we have to write down initial energy of the ball, so we have to consider rotational kinetic energy, translational kinetic energy, and also the potential energy. For if I choose this point to be zero level for potential energy, so it's zero potential energy. So this has both the rotational translational speed and the rotational speed. So I have to write these two terms, two kinetic energy terms, with the indices I, which means initial. And in the final case, it has, because it went up, it has now some potential energy, and also the linear kinetic energy and the rotational kinetic energy. Now, because this is a filled sphere, you look up the table for the moment of inertia, and it's 3 divided by 5 mr squared. And also because this condition is satisfied, so whenever I see VCM, I can write omega r, or alternatively, I can write, whenever I see omega, I can write, instead of omega, VCM divided by r. And that's what I did here. Instead of omega, I wrote VCM, so this is initial divided by R, and here VCM final, VCM final divided by R. And after this point, you can solve for the variable that the question is asking. It could be VCM, it could be R, it could be H, whatever it is. Okay, this is the last problem in this video. So here what happens is there's this rod that's fixed on the wall. It's initially horizontal, and it's so you just release it and it falls down to this point. So we have two questions. The first part is find the angular speed, the final angular speed when it falls down here. So We can find it from energy conservation. So we're going to write the initial linear rotational kinetic energies and the potential energy, and then we will write the final energies. So because this is fixed on the wall at this point, there's no linear energy initially or finally, right? There's no translational motion. It can only do rotation. As for potential energies, you can choose any point. I will choose this point as my coordinate system. So that means this is y equals 0. That means u equals 0 here. Now for the final case, the center of mass is here. So in this case, its potential energy will be, so what is this position? It's negative L divided by 2. So the potential energy will be mg negative L divided by 2. So we have the final potential energy here. Initially, we took potential energy to be 0 because we used this coordinate system. Now, what is the final rotational kinetic energy? Because it's doing rotation with certain angular speed. Now the rotational kinetic energy will be 1/2 I omega squared. Now I'm going to take this potential energy term to the left-hand side. It will come with, so the negative sign becomes positive now. And on the right-hand side, I only have this rotational kinetic energy term. Now this rod is rotated around its end. So which one should I use for moment of inertia? This one is when the rod is rotated around its middle point, but this one, 1/3, is when it's rotated around one of its ends. So I have to use this one. So moment of inertia will be 1/3 m times L squared, and L is the whole distance of the rod, or the whole length. So, and if you solve this equation for omega, which you will end up with square root 2 3g divided by L. And here g is the gravity of the Earth. Okay, in part B, find the tangential speed at the tip of the rod when the rod becomes completely vertical. So what is the tangential speed at this position of this point? Well, the definition of tangential speed at the distance r is r times omega. Now, what is r? R is here. This is the axis of rotation. And the point that we're interested in is this tip point. So the whole distance is L. So it will be L times omega, which we calculated here. So you can think of this L as square root L, and one of these cancel. So you end up with 3Lg square root 2. Okay, that's end of this lecture. So see you in the next video.